Thank you for watching our first series of ResearchLabX Research Primer. So now we'll move on to the second part, as promised, which is about basic biostatistics. So as the title suggests, we'll be covering the basic of biostatistics in this episode. First of all, we'll be doing a ground-up approach covering fundamental concepts in medical research, including hypothesis testing, p-value, how to interpret confidence intervals. We also explore some shortcomings on relying on statistical significance. Other than that, we'll be exploring how to choose the appropriate statistical test given a dataset. This will be really helpful as to the beginners, which I guess to me myself, who was a beginner, can be quite often overwhelmed by the complex statistical methodology sometimes required in medical research. So finally, we'll be looking at some common pitfalls when conducting medical research, most importantly the problem of multiple testing. So I hope this interests you, and without further ado, let's move on to discuss about all these topics. Okay, first of all, let us just look at the most fundamental concept of medical research, hypothesis testing, and the p-value. So I bet everyone has at some point of their career have heard about p-value, how it means significance and stuff, but you might not understand what it truly means. Okay? And we can even say p-values are the most commonly reported values in research. A p-value less than 0.05 often generates great excitement in researchers. And most of us will just rush to conclude that the results of the study are statistically significant. Is that true? What exactly does a p-value mean? Are there scenarios where the p-value might not be appropriate to use? So to find out all the answers, stay tuned and we'll be talking about it. Okay? First, let us explore a common scenario in medical research and see how the p-value is used when presenting the result of the study. So as you can see, this is a commonly seen study design of a randomized controlled trial, or RCT. Let us assume that the patient have been randomized into two arms, drug A versus placebo, and the outcome of interest is to see if drug A is useful in helping patients losing weight. So to do this, obviously we'll be looking at the primary endpoint of if there's any changes in the weight from the start of the study to 6 months later. So like all medical research, the aim is to see if the findings are meaningful. And this is accomplished via the process of hypothesis testing. So from the example shown from the previous slide, we're trying to investigate if drug A can result in a meaningful weight loss after 6 months compared to placebo to see if it's really useful, so we can use it for our patients, obviously. So all this starts with a null hypothesis, which is represented by the symbol H null, as you can see on the slide. What does that mean? It merely means that we are hypothesized that there is no difference between the control group and the patient receiving drug A in terms of weight loss, meaning they are equal. So drug A doesn't really cause any, meaningful differences. Second, we're trying to construct an alternate hypothesis, or H. So in this case, it means that the weight loss in the placebo group will be less than the weight loss in the drug A group, as you can see as point number 2. Next, using the data collected, we'll conduct the appropriate statistical tests. In this example of comparing weight loss of drug A versus placebo, we can use a 2-sample t-test. So don't worry, we'll be elaborating on choosing the appropriate tests in the later slide. Furthermore, in this case, we'll be using what we call a one-tail p-value. This is because we know the specific direction of the effect, which is the drug A, is expected to have more weight loss than the placebo group. Don't worry, we'll also be further exploring one-tail versus two-tail t-tests in the later slide. Okay, So once the appropriate data has been collected, as you can see on the slide, there's a formula. We can calculate what we call a t-value for the two sample t-tests. So this value will then use to find the corresponding p-value on the t-value distribution table. So I understand this might look quite complicated, quite hard to digest, but these steps usually will be performed automatically in statistical software like Stata or R or SPSS. Now that the p-value has been calculated, what exactly does it mean? The p-value actually just describes the probability of the observed outcome under the null hypothesis. For example, let's say in the weight loss scenario, again, let's go back to that. Drug A versus placebo. You can see on the slide, the mean weight loss in drug A and placebo groups are shown. And the p-value has been shown to be calculated as 0.01. This assumes the null hypothesis was true, and there is no differences in weight loss between the drug and placebo. And there's a 1% chance that this result will be seen. This is less than the threshold of 0.05. Hence, the results are concluded to be statistically significant. So it's usually conventional in medical literature to set the threshold to reject the null hypothesis at 0.05 for p-value. This just means that if the probability of witnessing the result under the null hypothesis are less than 5%, then we assume that that is unlikely and the null hypothesis is rejected. However, it's important to note that this 0.05 cutoff is arbitrarily decided and should not be the endpoint or most important data to present in the manuscript. We'll be talking about the limitation in detail in the later slides. Okay, so as discussed previously, we mentioned that in the example of the weight loss, drug A versus placebo, we use a one-tail p-value. What does that mean? Whether a one-tail or two-tail p-value is used depends on the hypothesis being tested. So one test p-value are used for directional hypothesis testing. So for example, if the treatment is known to produce a larger effect or a smaller effect. So going back to our previous example, the outcome of interest is if drug A will cause a large decrease in weight compared to placebo. Hence a one-tail p-value was calculated instead of a two-tail. On the other hand, we use two-tail p-value when the direction of the effect is unknown. So another example we can apply one-tail p-value is used, for example, a drug versus placebo. You can use it like scenario like weight loss or blood pressure or medication that can reduce cholesterol, as we will anticipate it to be downtrending, decreasing. An example for a two-tail p-value would be a study comparing, for example, two different drugs, drug A versus drug B, instead of using a placebo, and you want to know which drug causes more weight loss. In this case, the treatment effects is unknown to us before doing the study. So we use a two-tail p-value to investigate if there's significant difference in the weight loss comparing both drug A and drug B. So as I promised, we'll be talking about limitations of the p-value. So although you can see p-value in most of the literature, most of the studies, you can see in no matter if it's a high impact, low impact journal, I think it's really helpful for us to understand the limitation. And the number one point that I want everyone to understand is statistical significance does not equal to clinical significance. P-value itself doesn't provide any information about the effect size, like how large the effect was. This is because the p-value is largely affected by the sample size. So let us look at some scenario where the p-value can be misleading. So in cases where there is a large sample size, a small difference in effect can still result in a small p-value less than 0.05. For example, if 10,000 patients were to be included in each treatment arm, in the previous example, the difference in weight loss between the drug and placebo, if it's just 0.2 kg after 6 months, the p-value will still be considered as statistically significant due to the large sample size. But if you think about it, in real life, the difference might not be clinically relevant. So hence other values should be considered, including the confidence interval of the findings, which we will be talking in the later slides. Hence, other values should be considered, including what we call a confidence interval, which you guys might be more familiar as 95% CI. On the other hand, if the sample size is too small, it can cause a false negative result, as there might be insufficient statistical power to cause the p-value to be less than 0.05. So due to all these existing limitations of p-value, it's always important to consider alternate information, including study design, statistical test use, sample size, and importantly the confidence interval when reading and conducting medical research. Okay, so I understand along the video you might have more questions than answer. So don't worry, we'll try to explain one by one. So as mentioned in the previous slide, I mentioned confidence interval, and you might not be too familiar with it, or if you don't, understand the concept, don't worry, we'll be talking about it now. So as mentioned in the previous slide, p-value can be useful, but they shouldn't be presented in isolation because they can be influenced by other factors like sample size, study design. So confidence interval will come into play now. So what are them? What are they? So they are commonly presented in medical literature, I believe. You must have seen it before. But let's take a closer look at how they are derived to give us a clearer understanding of their meaning and utility. So what the official definition of a confidence interval is a range of value that is likely to contain the true value of a population parameter within a certain level of confidence. So let me try to break down to you what does that actually mean. So as you can see on the slide, let's say if we have a sample of 100 people that have a mean height of 170 centimeter and the standard deviation in the sample is 10 cm, what would the 95% confidence interval be? So the first step of calculating the 95% CI is to calculate the standard error of the mean, done as the formula shown, and in this case it will be the value of 1. And now you can see there is a picture of what we call a standard distribution. So we can all assume that all means of a value followed by a standard distribution, because what we call a central limit theorem, provided that the sample sizes are sufficiently large. So meaning that in a large enough study with a lot of patients, they will always follow a certain pattern, like a standard distribution, as shown on the picture. So in the standard distribution, 95% of the value are captured in the range of the true mean plus minus 2 standard error. So for our scenario, the 95% confidence interval will be the sample mean plus minus 2 standard error, which will be 168 to 172. So there you have it. The confidence interval for this study, for the example that we have shown, is 168 to 172. As much as I understand how this can be quite challenging mathematically, we do not have to remember them by heart, but merely we are teaching you today just to understand the concept so you know how to interpret it. So how do we interpret this value of 168 to 172 cm? What it actually means is we are 95% confident that the true mean height of the population lies between 168 to 172 cm. So it's also important to note that the confidence interval deals with means instead of individual. So here are some misconceptions that we would really like to clarify about confidence interval. So it's incorrect to assume that the 95% of the population has a height of from 168 to 172 centimeter. This is the most common misinterpretation of confidence interval. Once again, confidence interval deals with means instead of the individual value. Likewise, it's also incorrect to interpret this as there is a 95% chance that a randomly selected person from the population will have a height ranging from 168 to 172. So this merely means that we are 95% confident that the mean will lie between 168 to 172 centimeters. Only the mean height. So as much as confident interval can provide more reliability of our result, it also has factors that can affect the readings. So let us have a look at those. So first, sample size also affect the confidence interval. With a larger sample size, it will lead to a smaller confidence interval. So if we assume there are 10,000 patients in the sample instead of 100, this will lead to a much smaller standard error of the mean, subsequently a narrower confidence interval. Next, standard deviation of the sample also affects the confidence interval. So if the standard deviation of the sample is large, the confidence interval will always also be large. So this is demonstrated if we increase the standard deviation in the previous example from 10 to 20. So now we have a range of 166 to 174. Instead of previously it was 168 to 172. So finally, confidence interval also change based on the specific level of confidence. Let's say in this case, if you were to look at 99% confidence interval instead of 95%, based on the standard distribution, 99% of all sample means are captured within plus minus 2.6 standard errors of the true means. Hence, the 99% confident interval will be 176.4 to 172.6 instead of 168 to 172. Okay? I hope all those make sense so far. And take a break if this is too much for you, if you feel overwhelmed, before we move on to the next part. Okay? So I hope everyone is ready because we'll be talking about something really important, which is one of the main point of this episode: statistical versus clinical significance. So just to recap, we have explored how to calculate and interpret p-values and confidence interval. Let us take a look at why these values are helpful in interpreting and conducting medical research. So of course, let's start with the example again. So we can see this study published in JAMA in 2010, which aimed to investigate the effect of physical activity on weight gain prevention in women. So the table shown describes the mean difference in weight gains in the unit of kilograms over the period of 3 years. So they were split by low, moderate, and high exercise groups. So we can see the p-value comparing the low and moderate exercise group to the high exercise group is very low, at less than 0.001, indicating that high level of exercise are very effective at preventing weight loss over the period of 3 years. However, let us delve deeper into the result. We can see the 95% confidence interval was 0.04 to 0.2 kg, meaning that after 3 years, it is possible that high levels of exercise prevented up to 0.2 kg of weight gain compared to low exercise. So do we consider that a significant difference in weight gain in the real world? So that again leads us to the central issue that statistical significance does not equal to clinical significance. And other values should always be considered when interpreting and conducting research, which includes the sample size. As previously described, large sample size, such as in this study, involve more than 30,000 patients. That can cause that even small effect size to be statistically significant. However, we should always keep in mind that there are other factors at play in medical research so that we know how to interpret them. Okay. Okay. I hope the previous part will provide you some clarity in interpreting p-value and how you apply it, because it's a really important concept. So moving on, let us have a look at continuous versus categorical variable. And what is the two-sample t-test? So previously we mentioned the example of the weight loss randomized control trial. We'll be using a two-sample t-test. What does that actually mean? But for us to fully understand it, we have to first understand data types. So data can be categorized into two categories: continuous and categorical. So continuous data means data that can take on any value in a range. Things like height, weight, blood pressure, time measurement. So on the other hand, categorical data means data that can be grouped into fixed category. Things like sex, ethnicity, educational level. So rather than a reading, it's more of like groups and category. Okay? So other than determining the data type of the variable, for a continuous variable, we have to also consider whether the data is normally distributed. Common tests included t-tests, ANOVA, linear regression. They have an underlying assumption that the data is normally distributed. So before we conduct our analysis, we should check if the data is normally distributed, meaning if they follow the central limit theorem, a normal distribution. And let us have a look at some ways where we can check for a normal distribution. So as you can see on at the graph on the slide, we have a visual representation of the data. This is what we call a histogram. So all value of the variable of interest are displayed on the x-axis, and the frequency of how commonly these values are seen are displayed on the y-axis. So you might think that this histogram looks really familiar compared to the 95% confidence interval table, the normal distribution. So if the data is in a normal distribution, they will form a bell curve shape like this. So if the data visually differs from this distribution, such as if it is left or right skewed, or if the tails are too large, then it's very most likely that the data is not normally distributed. Alternatively, you can also visualize data using a QQ plot. So the x-axis are the theoretical quantiles, assuming that the data is normally distributed. The y-axis is the observed quantiles in the data set. So in a normally distributed data set, the QQ plot graph should be a straight line, something like the example shown here. If the line is overly skewed, then the data is likely not to follow a normal distribution. Okay, so you might thinking it's quite troublesome to look at graph. What if it's not accurate? So let's look at other option. Things like statistical tests to check for normality. So that includes the Shapiro-Wilk test for normal distribution and the Kolmogorov-Smirnov test. Both of these tests can easily be run in commonly used statistical software. So in terms of how to interpret it, so the test will output a p-value for a hypothesis that the data follows a normal distribution. So if the p-value for this test is less than 0.05, that provides evidence that the data might not be normally distributed. But again, like what we have previously mentioned, these tests are greatly affected by sample size. In a large sample size, there might be some slight deviation from normality that could be picked up by this test, although they are not significant. Hence, we should always present this value in addition to looking at the histogram and QQ plot of the data to determine normality. So, just to recap, we have gone through the type of data and to check if it's normally distributed. I believe we are ready to analyze the data. So have a look at the table on the slide. So we have first First of all, let's have a look at the test for continuous variable. So after checking if it's normally distributed, we can decide what kind of test to use. So if the data is normally distributed, we use parametric tests. So like the test listed, pair t-test, two sample t-test, or ANOVA. So correspondingly, if the data is not normally distributed, we'll use a non-parametric test. Things like Wilkerson sign rank test, Wilkerson rank sum test, Kruskal-Willis test. Additionally, we should also note that parametric tests compare the mean and standard deviation, while non-parametric tests compare medians and interquartile range. Okay? So next, for categorical variable, there is no need to check the distribution because there's only a limited number of values that can occur. So the tests for categorical variable are as follows, chi-square test, Fisher exact test, and also logistic regression. So in the next few slides, we'll cover when each test is appropriate. Okay, let's look at continuous variable. First of all, we see how many groups are being compared. If there are more than two groups, we use either ANOVA or Kruskal-Willis, depending if it's normally distributed or not. If there are only just two groups being compared, we need to check if the comparison is within group or between group. So let me give you an example to explain this. If we are looking at a trial of drug A versus drug B on an arbitrary score, the investigators compare the score at baseline versus 6 months later for drug A and drug B. So to check the significance of each drug on the score between baseline and 6 months, they should use tests for within group comparison as we are observing the same sample at baseline and 6 months later. So you can see, shown by the black colored brackets in the picture. On the other hand, if we are comparing which drug caused the larger decline in the score between drug A and drug B, we will use tests for between group comparison as we are comparing two separate samples. So this is shown by the red bracket in the figure. So for within group comparison, we have pair t-test and the Wilkerson sign rank test. For between group comparison, we have the two sample t-test and Wilkerson rank sum test. For categorical variable, we should first consider if the categorical data analyzed are correlated or matched. An example of matched or correlated data would be evaluating treatment response before and after treatment for the same set of patients. So if we are analyzing matched data, it's better to use McNamar's test. Otherwise, for independent categorical variables, we are using either the chi-square test or the Fisher exact test. So the choice between chi-square and Fisher exact test is based on the sample size. For the smaller size where any group that has less than 5 patients, the Fisher exact test is actually preferred. Otherwise, it's quite common to just use chi-square test for sample size bigger than 5. Okay, I believe at this point, you find yourself have listening to a lot of information, finding a bit overwhelmed. Let's go through some scenario to help with your understanding. So as you can see on example or practice number 1, we're comparing the BMI between smokers and non-smokers. What test should we use? So I'm going to give everyone 10 seconds. Feel free to pause the video. Read the information carefully and make a educational guess. Okay? Okay, so I assume everyone has interpreted the histogram. So now we'll just be reviewing the answer. So we can see the BMI is a continuous variable, and the bell-shaped distribution on the histogram show that it's normally distributed. Furthermore, we are doing a between-group comparison between smokers and non-smoker. Hence, in this case, we should use two sample t-tests. Okay, so now let's look at the next example. So what if we are comparing LDL by NECT group? So I'm just gonna suggest everyone to pause for another 10 seconds. Have a think about it. Okay. So I assume everyone has already done that. So we are once again looking at continuous variable that follows a normal distribution in our data set. However, this time there are more than two categories being compared, which are the different NECTs. So the appropriate test here is ANOVA test. Okay, so let's move on to our third example. Let's take a look at this example where there are 100 patients receiving treatment for high blood pressure, and the presence of high blood pressure has been split into yes or no. So the presence of high blood pressure before and after treatment is compared. Which test should we use this time? Okay, so again, pause your video for 10 seconds. Have a read about it. Okay, so I assume everyone has done so. So as the presence of high blood pressure has been categorized into yes or no. So in this case, it is a categorical variable. You can see the hypothetical cross table as shown in the slide. So this is an example of a pair observation as the same patient are being evaluated before and after treatment. Hence the preferred test in this scenario is McNamar's test. Okay, I hope the previous three exercise or example have been helpful. So let's go back to our old example of the randomized controlled trial of drug A versus placebo, which looking at the weight loss over a period of 6 months. So what we want to do now is to analyze whether drug A has caused statistical significant weight loss over the period of 6 months. The histogram show the weight loss by patient receiving drug A. So pay close attention to how the question is worded. What's the effect of drug A specifically on weight loss from the start of the trial to 6 months later? Okay, again, I suggest everyone to pause for 10 seconds, have a think about it, then we'll review the answer in a bit. Okay, so now we can see that we are analyzing a continuous variable that's not normally distributed. Hence, I think in this case, we have to use non-parametric tests. We also know that this is a within group comparison, as we are comparing the weight of patient receiving drug A at the start of the trial to the weight of the same patient at 6 months. So for within group comparison, the correct non-parametric test to use is Wilkinson sign rank test. Okay, but looking at the next slide, what if we instead looking at the same variable from a different perspective? So what if we are comparing weight loss in placebo versus drug A after 6 months? What test should we use? Pause for 10 seconds, think about it. Okay, so compared to the previous slide, this is between group comparison rather than within group comparison. So this is because we are comparing the weight loss between two distinct samples, placebo versus drug A, rather than just drug A itself for the previous example. So for between group comparison and non-normally distributed data, we should use the Wilkinson rank sum test. So finally, coming to our last example, what is the effect of smoking in a data set where we have categorized all patients into smoker or non-smokers on lung cancer? Again, pause for 10 seconds and think about it. Okay, so I'll be really pleased if some of you can solve it by now based on the knowledge that we have previously discussed. So in this scenario, we are analyzing categorical variables. Hence, the correct test will be chi-square test or the Fisher exact test if any cells in the cross table have sample size of less than 5. Okay, I hope those examples were helpful in consolidating your knowledge. Okay, so let's move on to the next session now. Okay, so I believe that was quite a good overview of choosing appropriate statistical tests. But then let us move on, and now we look at some of the limitation or more like an issue arise from that people should know when they are using statistical tests. Okay, so one of the common pitfall in medical literature, it is what we call multiple testing. And what's that? So every statistical test comes with a false positive rate, also known as type 1 error, where the researcher concludes that there is significant effect when in reality the effect does not exist. Because of the conventional threshold for statistical significance is set at p less than 0.05, the false positive rate for a statistical test in medical literature is around 5%. While this might seem low, when many tests are run, the chances for a false positive result increases actually. So to illustrate this point, if we conduct 100 independent statistical tests for hypotheses that are known to not have any real effect, there is a greater than 99% chance that at least one of the tests will produce a false positive finding. So how does this manifest in medical research? Let us look at some common pattern of analysis that can yield false positive result due to the problem of multiple testing. First, a study can test for many outcomes instead of a single composite outcome. For example, instead of just analyzing one outcome like overall survival, a study could split it into several separate outcomes such as infection, cardiovascular, cancer-related, or other types of mortality. Secondly, a study can stratify the patient population into many subgroups. An example of this is if the analysis is stratified by many age groups such as 5 years block. So we have less than 10 years old, 10 to 15, 15 to 20, 20 to 35 years old, which is actually pretty common in medical literature. Thirdly, a study can analyze several covariates separately with more than 20 predictors for the outcome of interest. Study can also analyze data at many time points. Okay, so all these methods sort of increase the number of statistical tests being performed, which in turn increases the chance of a false positive result, as illustrated earlier. So, when we are conducting medical research, how do we try our best to produce like accurate findings or conduct a research with integrity? So most importantly, we should define our analysis a priori. So what does that mean? Like subgroup analysis can be useful too for investigating interesting hypotheses, but we should be wary of conducting many subgroup analysis just to find a statistical significant finding. You know what is known as a p-hacking. So therefore, all analysis we conduct should be backed by clinical reasoning and be defined before the analysis has started. To provide accountability for this, we can specify what analysis we intend to run in the study protocol before the project has started. So this helps ensure that we are testing for real effect as much as possible and reduce the chance for a false positive result. Next, we can also consider the size of the p-value itself. A p-value close to 0.05 means that there is around 5% of the result occurring if the null hypothesis is true. Although this might meet the threshold for statistical significance under normal convention, we have to be more wary of this result if many tests has been conducted. Therefore, if we have conducted many different analyses and just one or two produce a p-value that is significant but close to 0.05, we should actually be more cautious before deciding if the effect is real. On the other hand, if the p-value is much lesser than 0.001, then there's a greater chance to support the finding. Last but not least, we should always consider results beyond the p-value, importantly the effect size and confidence interval. So by combining this value with our clinical knowledge, we can actually determine if the finding could actually represent a real effect or it's just another false positive result or affected by other co-founders. Okay, so to summarize whatever we have learned today, first we have gone through the basics of hypothesis testing. We've also covered how to interpret commonly reported values in medical research, including p-values and confidence interval. Next, we have covered how to choose the appropriate statistical test based on the data, if it's a continuous or categorical, or if the data is normally distributed. Finally, we've covered one of the common pitfalls, which is multiple testing, how it can cause false positive finding, and also explore common scenarios that lead to multiple testing, an important step to ensure the accuracy of our finding. So thank you very much for listening. I really hope everyone has learned something from our session, and I think it's really important for you to apply it to consolidate your knowledge. So up next, we will have the next episode coming, talking about advanced biostatistics. So make sure that you watch that episode to learn something more. Okay, thank you for watching. Hope you enjoyed the episode today, and ResearchLabX is here to help you to find the answers you need. We have a unique approach to research that emphasizes collaboration, creativity, and innovation. Our team is available to provide guidance and feedback throughout the process. If you are interested in learning more, contact us at ResearchLabX today using the link shown. Thank you.